Okay, so here we go. Next example, we're just going to pick up where we left off last time. We were looking at equations of planes and related type puzzles and questions. So so here in this question, we are given a point here, and we are given a couple of equations which we recognize as equations of planes. And the goal is to figure out what is this line that goes through the point A and that is parallel to both of the given planes that we have equations for. And specifically, not only do we want to identify this line, we want to parameterize that line specifically. Okay, so now again, remember the big picture strategy on this is if you have givens and if you have a goal, right? The problem solving tip here is to move forward from what you have, kind of work backwards, sort of reverse engineer backwards what's going to get you to what you need, and then hopefully you just meet in the middle, right? And very often this will work. So let's take that approach here. We're going to start off with our givens. We are given these two equations. And what can we conclude from these equations? What do we know? Can we tell immediately, even just by looking at these equations? Well, we can infer normal vectors, right? So this is one of our big conclusions from looking at equations of planes last time. The coefficients on the, if you will, left side of the equations, written in the appropriate form, give you the normal vectors for those planes. Okay, so we know now these normal vectors. Now, working backwards from our goal is a parameterization. Let's think through, what do we need to form a parameterization? Well, we're going to need a point on the line, but we're given that. So it's not really something we need. We already have it. We'll eventually need it, but we already have it, so we can set that aside for the moment. And what else do we need? We need a direction vector. We need a vector parallel to the line that we're going to try to parameterize. Right? So don't think of this as stated as here's two equations and we want to find a parameterization. Think of it instead as here's two vectors. I want to find this vector. Everybody with me? Okay. All right. Excuse me. And then, we have just a matter of how do we connect the dots? What is the relationship between these things? And you'll notice that these vectors, why don't I just do one at a time? This first vector here, well, it's perpendicular to this plane, which is parallel to this line, which is parallel to that vector. So there was a kind of a connect the dots there, but I think you can probably persuade yourself, just thinking geometrically, that means that this vector and that vector have to be perpendicular. Everybody buy that? Just a purely geometric appeal, right? And then likewise for the other one. So in fact, altogether, what we have here is that vector needs to be perpendicular to both of these vectors, and we know that the cross product will do that for us. So again, we kind of ended up sort of meeting in the middle. Well, we met almost in the middle. I had these and I needed this, and there was a one-step kind of, a very familiar one-step process to get from the two things that I have to the one thing that I need. Everybody happy with that? Cool. All right. So now there's an aspect of this solution that I just kind of waved my hands and said geometric appeal, right? We're going to be doing a fair amount of that in this class. But in particular, I made the observation that if this vector is perpendicular to this plane, and if the plane is parallel to this line, then the vector must be perpendicular to the line. Right? This is what I call a transitivity. A relates to B, B relates to C, and so I infer a relationship between A and C. So, all right, now I think in this case that's geometrically believable. right? Let me point out I did this last time as well in this previous example. I argued that, well, the plane is perpendicular to that normal vector, and the normal vector I directly computed with the dot product was perpendicular to the y-axis. And so, again, sort of connecting the dots, as it were, I infer a relationship between the plane and the y-axis. This time, perpendicular followed by perpendicular gives me parallel. Okay, so there are a bunch of possible transitivity type statements that one could try to put together along these lines. I mean, what if a plane is parallel to a line and that line's parallel to a different plane? Does that mean that the planes are parallel to each other? Or, okay, and then what about if I have a line parallel to, there's just a zillion, because you've got lines and planes and vectors, and then there's parallel, or perpendicular, or perpendicular, parallel. There's a bunch of different combinations. So what I want to say about these transitivities is be careful. They are not all what you would kind of hope from how you might write them down. Right? So some easy sort of like obvious, I'm going to say counterexamples. I mean, let's look at this vector v and this plane P. Now those are parallel. That plane P and this vector W, those are parallel. Just from the way it's written on the page, you might have some urge to conclude that V and W are parallel, but look at the picture, they're obviously not. And furthermore, once you think about the geometry of the picture, you realize there's no reason to think that they should be. Does everybody see what I'm talking about? Right? So, for example, in this section, what was it that led me to believe that I had this transitivity that I could argue here? Well, understanding just how geometry works, right? Just thinking through what the picture looks like. And so you're going to have to kind of be prepared to think through, well, let's see, if this is perpendicular to that and that's parallel to the other, and okay, it's a line or it's a plane, and you just kind of have to think through. And the rule is going to be you can make any transitivity argument you want as long as it's actually true. Right? So you don't have to prove your transitivity arguments, right? But you do have to think it through carefully and make sure that you're not accidentally saying something that's kind of garbage. Does that make sense to everybody? Okay. So again, mostly think of this as a warning. Here's another counterexample, by the way, another sort of like seems from how you've written it on the page here. It feels like, if P is perpendicular to Q and Q is perpendicular to R, you might kind of think that two perpendiculars ought to combine to make a parallel or something, but it doesn't, right? P and R, no relationship. They're not necessarily parallel, they're not necessarily perpendicular, they're not necessarily anything. So, again, warning. Okay, moving along. Let's talk about how to parameterize a plane. First of all, what does that even mean? Remember, we talked about parameterizations before, and in particular, they're a point generator. Parameters go in, points on your object that you're parameterizing come out. Okay, so what would it mean to parameterize a plane? Well, I'm going to point out that a single parameter is not going to do it. I know this because if you have a parameterization with a single parameter, we already understand that. That single parameter you think of as time. You have position as a function of time. That literally traces out a curve, right? Could not possibly trace out a plane. A plane is not a curve. Right, so one parameter is hopeless. It's going to turn out that two parameters is going to work just fine, and here is the way that works. Let's suppose that we know a point A, and let's suppose that we know a vector V and a vector W parallel to the plane that we're trying to parameterize. With these, I can generate any point X in the plane. And here's how I'm going to do it. I'm going to generate this point X by starting at A. My my given point in the plane. And then, roughly speaking, as I have drawn here, I'm going to need to go to some extent in the direction of V. Now, it won't be a single V. It might be a slightly longer vector than V, but some scalar multiple of V will give me, a vector the right amount in the direction of V. And then likewise, let's see here, and just to be clear, there's the V vector. Then likewise, I'm going to need from there to go an additional amount, some multiple of W. Again, probably not exactly W. I mean, depending on where this point is, right? I might need to go farther. Or, oh, hey, by the way, also possible. I might need, instead of going this way, what if my point was over here? I might need T to be negative. Or if my point was over here, I might need S to be negative, right? But that said, whatever purple point I need to get to, starting from A, some S and some T ought to do it. So this is a parameterization. You'll notice that, let me clean up the mess here. You'll notice that what I have here is positioned as a function of two parameters, S and T. And I think this is satisfying because if you think about it, just taking stock, parametric curves, well, I had one parameter and I made a curve which is a one-dimensional thing. Here I have two parameters and I'm generating a two-dimensional thing. Two-dimensional in the sense that it itself is two-dimensional. It lives in a three-dimensional world, of course, right? But the thing itself is just a surface, two-dimensional. Okay. Everybody on board? Yeah.
So given A, do any V and W parallel to the plane work, or do they need to be independent?
Yeah. They do have to be independent. But so they have to be non-zero, not pointing in the same direction. So there are many different parameterizations for a plane. And so different V's and W's will give you different parameterizations. Same plane. Everybody happy? All right. Okay, let's do one. Here is a familiar story. We've got 3 points, A, B, C. And those 3 points define a plane, like so. The unique plane that goes through those 3 points, let's presume they're not all sort of like along a line. And we want to find the parameterization. Well, here's our formula for a parameterization. Our parameterization is going to be pretty much that, just applied to the specifics of what I have below. So I'm going to need a point in the plane, and I'm going to need two vectors parallel to the plane. All right, well, here we go. Let's. Can I find a point in the plane? Yeah, sure. No problem. I've got 3 of them. Take your pick. Doesn't matter. Any one, whatever. I tend to like smaller numbers, so I'm going to pick A. But whatever. You can pick B if you prefer. Doesn't matter at all. Okay, 2 vectors now parallel to the plane, right? That's the next thing that I need, 2 vectors parallel to the plane. Well, again, we've been down this road before. We've used this tool before. When you have points in a plane, subtracting one from the other 2 gives me 2 vectors parallel to the plane. Very cool. And so, we're in business then. The point in the plane is A. The 2 vectors parallel to the plane are B minus A and C minus A. And here then is our parameterization. Yeah?
What does that X vector represent in this situation?
Yeah, so this is the output. X is the vector that's being generated. It's the point that's being generated by this parameterization. And keep in mind that's a parameterization's job, right? Is to generate points based on parameters. So given an S and a T, basic any numbers, it doesn't matter, right? Raw materials, think of it that way. Given S and T, this formula makes a point.
So even though it's a vector, it's technically a point.
we conflate points and vectors because context will always make it clear which, and it saves us the trouble of having to worry about having different formulas and different notations. Like, I mean, here's an annoying one, right? So we have a formula for how to add vectors. Have you seen the formula for how to add a point to a vector? Right. Right. So we don't want to have a separate formula. It's just easier to say if you find yourself looking at a point and a vector and you want to add them, interpret the point as being a vector, add the vector in the vector, and then reinterpret your result as a point. And I'm sure you've seen, well, in fact, here, check it out. I've added in this picture right here, A, I'm interpreting as a point, right? And then this SV, I'm interpreting as a vector, and the result is to give me another point. So rather than have, again, all these different separate formulas, it's just easier to kind of conflate them as convenient. Yeah. All right. Okay, moving along. Yeah. So distance problems. There's a bunch of versions of this as well. Again, I guess we could probably enumerate them all, but again, a better idea than enumerating and memorizing is to notice the tools that go into the way we're going to answer these questions that we are going to answer, get comfortable with the tools, and then recognize when new circumstances come up how those tools can be used in those circumstances as well. Okay, so we'll start off with let's see, we're going to have a point and a line that I'm going to presume is parameterized, and we want to find the distance here from that given point to that given line. Okay, so how to do this. All right, well, keep in mind the line is parameterized, so I have an x naught and I have a v. That's given. So here we go. Clever idea, I wish I'd thought of. Here's what you do. Subtract to form this vector w. Let's see here. Take its projection, which we know how to do from either, earlier this week, I'm pretty sure it was. All right, so we've got a vector w in orange, we've got its projection in red, and notice the distance that I'm interested in is just the magnitude of this vector here, namely their difference. All right, so you subtract your w minus the projection. That gives you the perpendicular, you might say the perpendicular part of that orange vector, and the distance is its magnitude. Is everybody good with that? Everybody see this sort of the strategy there? I mean, the big picture here is that in some sense w represents moving from the line to the point, but it does so in this weird way where there's a parallel movement along the line. That's not what we're interested in. We're interested in the perpendicular motion, if you will, from the point to the line or vice versa. And so basically taking that w and then just subtract off the part that you don't want, right? I'm intrinsically not interested in parallel movement along the line. I'm intrinsically interested in perpendicular movement away from the line, and so that subtraction does it for us. Okay, so again, you could memorize the formula. I suggest you don't. I suggest you understand the trick and use the trick as a tool. Okay. All right. Okay, now the next example, same question. Distance from a point to a line. And now again, real quick, why are we looking at the same question? Why do we need two different methods for solving the same question? And the answer is because we're not interested in the question. We're interested in the tools. Okay, so here we go. By the way, this is a weird one. But this is a weird one, which is an example of a strategy that gets used surprisingly often in math. I've seen the following strategy used in this course here in several places, but then also in other fields of math, surprisingly often. And here's the big idea. When you're interested in something, compute something else. Do it two different ways. Compute the thing that you don't care about. 2 different ways. And if the thing that you're interested in happens to show up in one of those calculations, then if you think about it, the thing you were not interested in that you computed 2 different ways, well, the answers that you got, these 2 different answers, being as they are the same, you can then just solve for the thing you're interested in. Right, so that's the big picture strategy. Details I'm going to go through momentarily. I'm just trying to hit the big picture first. But find something that relates to what you're interested in, compute it twice, and then solve for what you want. All right, let's do details. Starting with this area. It's going to be the thing we're going to compute twice. We're not interested in this area, but we're going to compute it anyway. And first formula for that area, now this is a flashback to high school geometry class. If you have a parallelogram, actually there's a variety of different shapes that this applies to, but height times the base. Right, and recall previously this vector that represents the base, that's the projection, and so the length of that base, the magnitude of that projection vector, is the length of that base. Everybody good? Everybody remember high school geometry, height times base and all that? Okay, all right. So, great, we just successfully computed something we're not interested in. Let's do it again. Again with the area that we don't actually care about. Okay, here we go. How are we going to compute this area this time? Well, there's the projection vector and there's this W vector. Again, we've computed those already, right? And projection cross the original. I got those backwards. Oh my God, that's going to confuse me. Let's see here. The projection cross the original difference vector, right? This is a cross product of the 2 edges, the 2 vectors defining that parallelogram, assuming this is 3-dimensional. And that magnitude gives you the area. So again, we've computed something that we are not interested in. But having computed that thing we're not interested in twice, I know that these 2 things are equal, and again, as we previously observed, that allows me then to solve for the thing that I actually want. So lovely little trick, wonderful strategy. Again, it comes up all the time. You can look for opportunities to use this. By the way, one of the proofs that I skipped back in the section about cross products was another one of these things where I computed something I was not interested in, but I did it twice, and the thing that I was interested in was part of one of those calculations. All right. Okay, let's see here. The distance between parallel planes. Another little clever trick. Here's the distance I'm interested in. Notice the distance between 2 planes is a perpendicular distance. Right? That's the only reasonable thing to define as distance between 2 planes. Here's the strategy. You take a point in each plane, you subtract. This is not the distance that I'm looking for, because I mean, look, I picked these points randomly, so this vector here is at some weird angle, and it's longer than the distance is that I'm actually looking for. But that difference vector, if I look at its component in the direction I care about, right? That component in the direction I care, the component of orange in the direction of blue is exactly what I need. There you go. Oh, absolute value. Because again, distances have to be positive. So, absolute value. Everybody happy? Yeah, go ahead.
So do you have to unitize n then?
Well, not really, and kind of. So the definition of component it allows for n to be unit vector or not unit vector, either one, right? But if you look at the formula for how to compute component, it ends up being dot product with the associated unit vector. So in some sense, kind of morally, like it ought to be a unit vector, but realistically in practice, such as here, right? I mean, when I write down a normal vector, most of the time it doesn't happen to coincidentally also be a unit vector. So we have to have our definition flexible enough to deal with the fact that this could be non-unit, but then you got to dot it with the associated unit vector. Yeah. Everybody happy with that? Okay. All right. This next one is weird. Also an example of a strategy that's very often useful in math. Very often when you're solving a math problem, you can try to relate it to a question you already know the answer to. And that's what we're going to do here. The question at hand is going to be how to find the distance between two skew lines. Okay, so skew lines like so are lines that don't intersect and that are not parallel. So lines that have nothing in common. Just weird, random, unrelated lines. And if you have such skew lines, you can imagine there's a sort of a distance between them, sort of the closest possible distance between any pairs of points on any of the lines. So how to compute that? Here's the insight, the clever move. Again, I did not think of this. Somebody showed me. Look at the two direction vectors. If I were to take a cross product of those two direction vectors, that cross product would be perpendicular to V1 and perpendicular to V2 because it's a cross product. If I were to make that a normal vector, like so, and if you think about it, that then is going to give me a pair of planes, one of which contains L1 and the other of which contains L2. Right? Because what would I need for there to be a plane containing L1? Well, I would need the plane to have a normal vector perpendicular to the plane, but wait a second, the normal vector is perpendicular to the plane, and the plane is parallel to the line. There's another one of these transitivities, right? Then I would need for the normal vector perpendicular to the line, which it is. Likewise for the second one. Okay, so what have we done here? We haven't solved the problem. The problem was to find this distance, but we have translated the new question into an old question. How do I find the distance between these skew lines turns into how do I find the distance between these two parallel planes? And again, that was the last example that we did. That was this formula up here. So reduced to a previously solved problem. All right, everybody see the strategy there? Sometimes that kind of thing helps out. Okay, moving along. So that's section 1.5. Let's see here, already did 1.6. First day of class, so that's old news. Moving on to 1.7. So new coordinate systems. The first thing I want to say about the coordinate systems is let's say a few words about our existing familiar coordinate system, rectangular coordinates. We take it for granted. We treat it as a given, and importantly, it's not. The rectangular coordinate system is a choice. Now, it's bonkers convenient. Right, it's definitely the best choice. If you had to have just the one coordinate system that you're allowed to use, for sure rectangular, no question. Right, it's just extremely natural. Among other reasons, consider the following: if you have a point in the, let's say, two-dimensional plane, notice there is a uniquely unambiguously defined x-coordinate. By the way, mathematicians very often use an exclamation point to represent unique. So we have a unique x, we have a unique y, and thus a unique set of rectangular coordinates. So this is what we mean when we say rectangular coordinates are unique. You give me a point, literally, its rectangular coordinates are unique. There is only one way to write that point in rectangular coordinates. Okay, bad news. This will not be the case in our new coordinate systems. It's weird, and the very first time I heard this, I thought, well, that's outrageous. What use could it be? Right? Well, it turns out it ends up being useful. So, nevertheless, though, that's disappointing and weird. The other thing, and again, we've gotten so accustomed to rectangular coordinates, we almost kind of take the following for granted, but really nice conveniences of how the algebra plays out. The coordinates are the coefficients in a linear combination of the standard basis vectors. Well, this is ultra handy. If you take a linear combination of vectors written in rectangular coordinates, and likewise just take the corresponding linear combinations of the individual coordinates. Works great. It's just lovely. Okay, again, no such luck in polar coordinates or spherical or any of these others we're going to do. Okay, so we have to get accustomed to the idea of weird. So diving in now, here is our picture. I think a lot of y'all may have seen polar coordinates before. If not, here's the idea. The idea is that theta defines an angle. The angle is measured counterclockwise, starting at the direction indicated by the positive part of the x-axis, going counterclockwise from there. That's called theta. And then, now I'm going to commit a little math crime here and then confess later. R, I'm going to say, is the distance that we go in that direction. How far do we go in that direction? And if you give me a theta, defining a distance, and an R, defining how far to go, then notice that gets me to a location. And so I could say, all right, well then this theta and this R, for whatever reason, we typically write r comma theta, whatever, are the polar coordinates for that point. Is that cool? All right, now let me confess. I said r is a distance. It's not. And it's annoying, but there's this awkwardness of the fact that the word distance, that's an intrinsically positive thing. You will never pull up Google Maps, how far is the distance from this location to that location. It will never give you a negative number, right? Ever. Okay, well, am I saying when I say r is a distance, am I saying that r is intrinsically positive? No, that's the problem. It's not. R could totally be negative. If r is negative, and you think about it, if that's the direction we're talking about, then going in that direction, going farther in that, the more positive the number is, the more you go that way. Well, the more negative it is, the more you just go the other way. So negative r just has you going backwards from that direction indicated by theta. And there's nothing wrong with that at all yet. Now, foreshadowing. It's going to turn out in a couple of months, or at least a long time from now, we are going to find that some legitimate problems are going to come up if we continue at that time to allow r to be negative. So at that time, once we have a legitimate reason to rule out r being negative, then we will. But until then, r is perfectly allowed to be negative. Okay. All right. Now, real quick, I think it's nice to think of r and theta in relation to a function. So this is what I like to call the polar coordinates conversion function. Let's call it G. The P subscript is just a reference to polar coordinates. And so we can think of r and theta as just being the inputs to this function. And given an r and a theta, given an r and a theta, there is a corresponding x and a y. So, so saying that differently, x and y are functions of r and theta. And what those functions are as formulas is actually pretty straightforward. We can totally see how that works out by looking at this little triangle right here. Right? And the trig of that triangle gives us these formulas right here. X is our cosine theta, y is cosine theta. Now, I trust that y'all are all proficient with your trig, and so I'm sure you can think that through. But if you're not sure, then it's a good thing to think about and make sure that you're comfortable with. Come to office hours and ask questions anytime, of course. All right, is everybody okay? Yeah.
Is there like some convention for r and theta? Like r can be negative and theta can be like any angle, right? But is it like, do we say like usually r is positive and theta is 0 to 2 pi, or?
Yeah, I mean, you can, anyone who wants to can say, for my own personal reasons, I'm going to make the following choices. I'm going to insist that r is positive. I'm going to insist that theta is always between 0 and 2 pi. And you can make those choices. But there's always going to lead to problems of some form or another. And so I think it's better to just leave it all open and then make choices appropriate to the circumstance when you encounter the circumstance. So there's certainly no standard like restrictions that everybody agrees to. Yeah, so it's good to leave it open. Is that cool? Yeah. All right. So moving along. Yeah, tragically, not unique. So here's an example. Let's think about this point right here. That point you can think of as relating to this angle, theta. And let's see here. It looks like I've indicated that this thing has a distance of 5 from the origin going in that direction. So, okay, so this point in the r theta plane, that r and that theta go to that point in the xy plane. So, or said differently, you could think of these as the polar coordinates of that plane, the xy plane. Now, here's what's weird. The failure of uniqueness. What would happen if I were to take this theta value and just add 2 pi to the theta value? Well, I'm going to get a completely different set of polar coordinates, right? But what happens in the xy plane? Well, if you think about it, if you're adding 2 pi to the angle, that means I'm going to take the direction I was in and I'm going to go around an additional full turn, thus leaving me pointing in exactly the same direction. And so, keeping my r at 5 gives me now a new set of polar coordinates that gives rise to exactly the same point in the xy plane. So this is one of those failures of uniqueness. I could think of this as the polar coordinates of that point, or just as legitimate, I can think of this as being the polar coordinates of that point. And you could add another 2 pi, and you could add another 2 pi and another 2 pi. You could add as many 2 pi's as you want, right? Integer multiples of 2 pi, of course. All right, and that's not all. It gets weirder. What if I just added 1 pi? A half turn, as it were. Well, if you do a half turn, notice that gets you going what you might call exactly the wrong direction, right? It's diametrically opposed to the direction in some sense you should be going. So, okay, well, here's the thing. If you're going the exact wrong direction, if you let r be negative 5, right? So let r here now be, all right, highlighter. I'll let r be negative 5. Then, okay, now this point also just as well gives you the exact same x and y. And so said differently, this is a whole nother alternative polar coordinates for the exact same point. Anybody with me? It's weird. So yeah, lots of failures of uniqueness. Oh well. Yeah, there we go. Okay, here's another little thing to be worried about. This is just a notational thing. I don't want to get bogged down in this, but if you were to write down, let's say, 2 comma pi over 6, I mean, you might think it's pretty clear that what you meant by this was that pi over 6 is, come on, it's the angle. It's pi over 6. It's 30 degrees, right? I mean, that's the most common usage of pi over 6 is to represent an angle, pi over 6. And so you could think, okay, well, obviously I meant that angle, and then 2 being the r means I'm going to go a distance of 2 is positive, in that direction, and that therefore these are in reference to that point. And you might think, well, that's perfectly clear. The problem is, pi over 6, in addition to being a number that regularly refers to a nice, friendly angle, is also a perfectly valid real number. And 2 is a perfectly valid real number, and there is absolutely no reason why it couldn't be that this was your x and this is your y, which would have you let's see here, x is 2 and y is pi over 6, and this seems weird, I suppose, but nevertheless, maybe this is referring to that, and it could be either one. Right, so that's a problem, because if you write something like 2 comma pi over 6, now it's unclear. Your reader doesn't know which one of these points you're talking about. You're talking about this location where the numbers you supplied are polar coordinates, or this location where the numbers you supplied are rectangular coordinates. From what is written right here, could be either. So this is an easily resolved problem. Let's suppose, for example, that I didn't mean that. How would I eliminate the possibility that I'm talking about rectangular coordinates? Well, then just say so. You can just write down literally r comma theta equals. And now it's perfectly clear these are polar coordinates. Now I know I mean exactly that. Ambiguity removed. So heads up, it's a minor little inconvenience, but having an ambiguity in what you're writing can be a problem. Okay. All right, now here's a more serious problem. This is a wrong answer situation. Not hard to persuade yourself that we have these relationships, additional relationships between r, theta, x, and y. And again, it's just a little bit more sort of geometry and trig on the same triangle that we used here to find previous relationships we wrote down. Okay. There is a temptation to want to take these equations that I have here in orange and solve for r and solve for theta. Right? But now let me just point out what's fundamentally flawed about that idea. If you say you're going to solve for r in this equation, what solve means you're going to get r is and have a single value. That's what it means to solve, right? R isn't unique. There's actually multiple values of r, so you can't solve, really. Get right down to it. And likewise, with theta, there's a bazillion different values of theta that might be the coordinates that we're looking for. Right? So I think what is a much better idea is just leave the equations in this form. Right? Write down, take the point that you're interested in, and in this question, I'm going to be interested in this point. Oh gosh, I wanted that in pencil mode. Sorry. This point right here. Right, there it is, -1, -1. That point, take these numbers, plug in to these formulas, and then write down what your candidates are, right? And so it's not hard to persuade yourself that, and again with the highlighter now, r could be either one of these values, and theta could be either one of these values. Okay, now where students will make a mistake is they'll say, okay, look, I don't want to do anything fancy like going multiple times around, so let me just pick the, the basic values. Right, I'm going to pick r to be positive square root of 2, and I'm going to pick theta to be pi over 4. I mean, I've got a bunch of choices, so let me just pick the easy ones, and then we'll just declare victory and move on down the road. And that's wrong. Wrong. Because, I mean, think through the geometry. Theta is pi over 4, goes that way. Right? R equals square root of 2 means go a distance of square root of 2 in that direction, and that gets you to, yes, this point right here, which is not the point that we were interested in. Does everybody see what happened there? I mean, it just isn't. So, if you make the mistake of, moving sort of too fast and loose through the algebra, in fact, I would say it's a mistake to take any sort of purely algebraic point of view on this and just say, okay, well, r is the square root. Square roots are positive, and okay, so if you just kind of always write down the positive square root and always pick, the arctan, you're going to get wrong answers about half the time. So not okay. What you should do instead is once you have your options enumerated, think through the geometry. Right? So for example, you might say, okay, how can I make use of pi over 4? Well, there's pi over 4. That's the direction, pi over 4. If I take this direction, which of my options on R will actually get me to the point that I am actually trying to represent? I'm trying to represent this point here. And you can see from the picture, this point's over here. That direction point's kind of the wrong direction, if you will. And therefore, I'm going to need to pick the negative value of R. And that gets me the correct point. Or vice versa, if you prefer. What if I chose the 5 pi over 4? That gets me going what you might call the correct direction. Cool, now I'm going right at it. How far do I need to go in the correct direction to get to that point? Well, I'm going the correct direction, so square root of 2. And that also gets you to the correct point. Everybody okay with that? So again, just be careful. Again, reminder, notice there's nothing weird about this example that I didn't have to go to a ton of trouble to manufacture some super obscure scenario. This is just a point, right? An easy point, and you have to think through the geometry in order to make valid choices about the polar coordinates. Okay. All right. Moving along. Okay, we have 2 minutes. You'd be surprised how quick this part is. How do you interpret an equation in polar coordinates? There's a bunch of examples I'm going to do here. The first two are ultra quick. R equals 3. If you think about it, it says right there that R is positive because it's 3, which is positive, which means that R is a distance from the origin. And so this says, look, I want to know points whose distance from the origin is 3. And geometrically, that's easy. That's a circle. So we already know what this is. Now, that said, what if I didn't notice that? How would I take this and turn it into rectangular coordinates? And there's a trick here. And again, tool for your toolbox. I did not think of this. Somebody showed me. Now I'm showing you. Okay, so the trick is, in this case, square both sides of the equation. And notice that having done so, we get an r squared, about which I already know a conversion into rectangular coordinates. That's x squared plus y squared. And that gives me an equation that I recognize from high school algebra class is a circle of radius 3. So same answer, but with an algebraic sort of path of getting there. And the trick, the little slick move that made it all work, is this right here. Looking and seeing that this equation, if I square both sides, then I get a foot in the door. All right. There is a different trick for this equation. Now this right here, I could say, look, I understand the geometry of theta. Theta means a direction, so theta equals pi over 3 means that way. Oh, of course, r could be negative, so it means that, oh man, missed. It means erase that whole line. And again, we got lucky. Sometimes you get lucky. If you don't, what do you do with this equation to get to something familiar? The clever move, what somebody showed me is take the tangent of both sides. And if you take the tangent of both sides, again, you get to something where you have a freebie conversion. And that turns your equation into rectangular y equals a multiple of x, which recovers what we already knew. Okay, that's a good place to stop. Y'all have a great weekend. See you on Monday.